Hello everyone, I'm Raythan from Group 5 and I will explain about the summary of this experiment 5, which is bending moment. So let's start with the summary. The goal of this experiment is to determine the beam's bending moment. Shear force is defined as the algebraic sum of all vertical forces operating on either side of loaded beam at any location. Shearing of the beam and the point where it is working is the net result of the shear force. Shear forces are considered positive if they produce a clockwise moment, and they are considered negative if they cause an anti-clockwise moment. The sum of the moments attributable to all vertical forces operating on either side of the point on the beam can be expressed as the bending moment at any point along the loaded beam. The beam is bent by the bending moment. The anti-clockwise moments caused by the weights operating to the left of the section are believed to be negative, whereas the clockwise moments are assumed to be positive. The beams are connected via a joint, resulting a frictionless hinge. With a 150 mm lever arm, an anvil has a moment of resistance around the hinge suspended spring balance. 3 load hangers on the beam cause the load into the beam, and the 2 bearings on the stand stabilize the beam, resulting in a spring balance measurement. The spring equilibrium reading would be 150 times the calculated bending moment in Newton millimeter after the correction. The bending moment at the end of the beam, which for the loads with specified configuration showed a little divergence from the theoretical values, and was determined by the experiment results.
Hello everyone, I'm Pavitra and I'll be explaining about the introduction and also the theory. For the introduction part, the objective in this experiment is to measure the bending moment of the beam. Shear force is a force at any point along a loaded beam, may be defined as the algebraic sum of all vertical forces acting on either side of the point on the beam. The shear force has the net effect of shearing of the beam and the position where it is working. If shear forces produces a clockwise movement, they are considered positive. If they produce an anti-clockwise movement, they are considered negative. Bending moment at any point along a loaded beam may be also defined as the sum of moments due to all vertical forces acting on either side of the point on the beam. The bending moment tries to bend the beam. Clockwise movements due to loads acting to the left or the section are assumed to be negative, while anti-clockwise are positive. Are divided into 2 parts, which is A is smaller and B is a larger part. A joint connects the beam, forming a frictionless hinge. An anvil has a moment of resistance around the hinge slung spring balance with a 150 mm lever arm. The spring balance reading is recorded while 3 load hangers on the beam to cause the load into the beam and 2 bearings on strands are to stabilize the beam. The adjustment in the spring equilibrium reading will be 150 times the calculated bending moment in Newton millimeters. From the experiment result, the bending moment at the end of the beam, which for the loads with specific configuration showed a slight deviation from theoretical values. For the theory part, when a beam is loaded by forces or couples, internal stresses and strains are created. To determine the stresses and strains, the internal forces and internal couples that acts on the cross-section of the beam should be determined first. Consider a cantilever beam acted upon by a vertical forces P, like shown in figure 1a. Now imagine that the beam is cut through at a cross-section of XX, like shown in figure 1b. For the left-hand part, which is part A, the shear force Qx, shown in figure 1b, which is the blue box, and the bending moment in figure 1c, which is the red box, are assumed to be positive in direction as shown in figure 1b and 1c respectively. The positive direction is vice versa if the right hand part B of the beam is considered. For vertical equilibrium of part A, there must be a shear force Qx acting as shown in figure 1b, which is the blue box, and equal to negative Ra. For vertical equilibrium of part B, the shear force Qx evidently acts as shown and has the value of negative RB. For equilibrium of moments for part A of the beam, mx equals to RA times A, which is equation 1, and equilibrium for moments for part B of the beam, mx equals to RB times B minus P in bracket B minus 1, that is the second equation. Thus, the third equation will be mx equals to negative BP minus RB plus P1 is equals to negative BRA in bracket plus RA in bracket A plus B, and the equation 3 will be RA times with A. Therefore, the moment of the beam at any length along the beam is as in equation 3.
Okay, hello, my name is Siti Nurhasha binti Suhaimi. So today I'll be explaining to you about the experimental procedure in experiment 5. So the first one, there's two parts in this experiment. Okay, so the first one for part 1 is the beam was set up so that the bearing pin in part B is 300 mm from the left hand support and 600 mm to the right hand support. The second one, one load hanger was placed on the middle of the smaller part A of the beam and one on the larger part B, and the third one at the joint just over the bearing pin, which is in the groove provided. Okay, so the third one, the two parts of the beam were aligned using the adjustment on the spring balance, and the initial reading was recorded using table 1. Okay, so for the fourth one, the 10 Newton, which is 1 kg weight, was hanged on part B. The beam was realigned and the new readings on spring balance was recorded using table 1. The difference between the two readings is the effect when we apply the 10 Newton, which is 1 kg weight, on the beam. The distance is recorded using table 1 from this weight to the right hand support. Okay, so the last one for the part 1 is the procedure was repeated by using the hanger over the bearing pin and then the hanger on part A. Finally, the whole procedure was repeated by using a 20 Newton, which is 2 kg load. For part 2, the 3 load hangers were placed as desired in figure 4. The beam was aligned and the initial reading of spring balance was recorded using table 2. Okay, secondly, the weights were put on all the 3 hangers, the beam was realigned and the new balance reading was recorded using table 2. So the last one in the part 2 is the experiment in part 2 was repeated with the different positions and loadings, which is in figure 3. The new balance reading was recorded using table 3.
Assalamualaikum and hi everyone, I'm Anissa. In this experiment, I will explain the results and discussion part. So as we can see here, this is table 1, data for bending moment at C, which is MC for the load configuration in part 1. So here we have load for 0N, 10N and 20N, and we have to calculate the balance reading, or we call it net force in Newton for load at P1, P2 and P3. So from the calculation of balance reading, we can calculate the theoretical value also for load 10N and 20N. So for the sample calculation for part 1 in table 1, to calculate the balance reading or net force in Newton, value load at 10N minus value load at 0N, which is 24N minus 20N, we get 4N. So from this value, we can calculate the bending moment, which is 4N multiplied with 150 mm, and we get 600 Newton millimeter. So to calculate the theoretical value of bending moment, the total of MB equal to 0, and RA multiplied with 900, which is the distance, minus 10 multiplied by 800 equal to 0. And from this calculation, we can get RA. And to calculate the MC, the RA value multiplied with 300 minus 10 multiplied with 200, and we get 667 Newton millimeter for load 10N. For table 2, this is the data for bending moment at C, which is MC, for the load configuration in part 2. So here we have loading for 0n, and at P2 equal to 5n, and at P1 and P3 equal to 10, and at P2 equal to 5. To calculate the calculation in part 2a, when P1 and P3 equal to 10 and P2 equal to 5, the balance reading is 36 Newton minus 80 Newton, and we get 18 Newton. From this, we can calculate the bending moment, which is 18 Newton multiplied with 150 mm, and we get 2700 Newton millimeter. From this value, we can compare with the theoretical value. So to calculate the RA, we have to put MB equal to 0, and we get RA 15.56 Newton. To calculate the MC, the RA multiplied with 300 minus 10 multiplied with 200 equal to 2668. So, Table 3 shows the data for bending moment at C, which is MC, for the load configuration in part 2. The difference is the position and loads is different from part 2A. So in this data, we have loading for 0n, and for the second one is P1 equal to 5 and P3 equal to 12 Newton. And the last one, if P1 equal to 5, P2 equal to 10, and P3 equal to 2 Newtons. And we have to calculate the balance reading, net force, bending moment, and bending moment for theoretical value. For the sample calculation for part 2b, we want to find the last one, which is when P1 equal to 5, P2 equal to 10, and P3 equal to 12, also for P3 equal to 2. So to calculate the balance reading, value in this case we calculate for 36 Newton, and 36 Newton subtract with 20n, we get 16n. From this value, we can calculate the bending moment, which is 2400 Newton millimeter. And to compare with the theoretical value, we have to calculate the RA. So the total of MB equal to 0, and RA we get 11.56 Newton. From this value, we can calculate MC, which is... Okay, so we continue with the bending moment diagram. So for P equal to 10N, the bending moment diagram, which is bending moment Newton millimeter versus distance in millimeter. Based on this graph, we can see that in vertical axis is bending moment, and at the horizontal axis is distance. So when the distance is 0 millimeter, the bending moment also 0 Newton millimeter. And when the distance 100 millimeter, the theoretical value is higher than the experimental value, and which is for the theoretical value is 667, and the experimental value is 600 Newton millimeter, which is 67 Newton millimeter higher than experimental value. So when the distance is 900 millimeter, both of the experimental and theoretical value is 0 Newton millimeter. Okay, for P equal to 20 Newton, when the distance is 0 millimeter, the bending moment for both theoretical and experimental value is 0 Newton millimeter, and at the distance of 100 millimeter, the theoretical value is higher than experimental value, which is 1334 compared with 1200 for experimental value. And at distance 900 millimeter, both of the theoretical and experimental value is 0 Newton millimeter. Okay, continue with the discussion part. First, the question is, when the load was doubled in part 1 of experiment, did the bending moment double? Okay, based on the graph of bending moment plotted from the calculation in part 1, the value of bending moment is directly proportional to the force that is being applied. It shows that when the load increases, the bending moment also increases. Additionally, when the stress is added, the bending moment will be double the original value. For instance, when P1 equal to 10 Newton, the experimental value of bending moment is 600 Newton millimeter, while the theoretical value is 667 Newton millimeter, and followed by the experimental value of bending moment for load 20N, which is 1200 Newton millimeter, and the theoretical value is 1334 Newton millimeter. Both values are twice the value of. Next, the question is, compare the average figure for each of the experiment by using the bending moments, values obtained from the experimental and theoretical value. Use either a ratio or percentage error. So in this case, we calculate for the percentage error. To calculate percentage error in percent, the experimental value minus theoretical value divide by theoretical value in modulus and multiply with 100%. So in this table for part 1, we compare the experimental value with theoretical value at P1, P2 and P3 for load 10N and 20N. So to calculate the P1 for 10N, the percentage error in percent equal to 600 minus 667 divided by 667 in modulus and multiply with 100%. So the result is 10.04%, followed by P2 10N and P3 10N. So from this value, we can calculate the average percentage error when load is 10N. After doing the calculation, we get the average value of loads 10N is 10.01%. So the average percentage error when loads 20N is 10.01% also, same as when the loads is 10N. So for part 2A, this table we compare the experimental value and theoretical value to calculate the percentage error. So for the sample calculation, when P2 is 5N, the percentage error is 1050 minus 1000 divided by 1000 in modulus, multiply with 100%. So we get 5%. And for part 2B, also same as part 2A, we want to compare the experimental value and theoretical value by percentage error. So for when P1 equal to 5N and P3 equal to 12N, the percentage error is 1500 minus 1934 divided by 1934 in modulus, multiply with 100%, and we get 22.44%. So that's all from me. Thank you.
So let's move on to the conclusion part. In a nutshell, the experiment's goal of measuring the material's bending moment was accomplished. The bending moment at C for the loads with specific configuration revealed no significant variation from theoretical values in the experiment that we conducted. At 10 Newton at P1, P2 and P3, the bending moment at C was 600 Newton millimeter, 1800 Newton millimeter and 900 Newton millimeter respectively, whereas at 20 Newton it was 1200 Newton millimeter, 3600 Newton millimeter and 1800 Newton millimeter. When the load is 0 Newton, P2 is 5 Newton and P1 equals to P3, which is equals to 10 Newton together with P2 equals to 5N, the bending moment at C for load configuration at part 2 was 0 Newton millimeter, 1050 Newton millimeter and 2700 Newton millimeter respectively. Furthermore, in part 2, the bending moment for 0 Newton was 0 Newton millimeter, P1 equals to 5 Newton with P3 equals to 12 Newton was 1500 Newton millimeter and P1 equals to 5 Newton, P2 equals to 10 Newton and P3 equals to 2 Newton was 2400 Newton millimeter at various places and loads. Furthermore, the bending moment doubled when the weight was doubled. The experiment values of bending moment obtained was so close to the theoretical values with minimal percentage error due to the unavoidable experimental errors. Hence, the theory of bending moment can be concluded as valid and accepted. That's all from us. Thank you.